So today we have to talk about the three things. The one is about the dissimilar metal joining using the friction welding, and thereafter we'll try to talk about the typical welding parameters which are used for the different for joining the similar as well as the dissimilar metal combinations. That will give you idea of the kind of things that we need to control for the similar or dissimilar metal joining, and the kind of issues that are encountered. Of course, that will be about that we'll be talking first, and thereafter we'll try to see uh, what are the various configurations and the combinations of the relative motions which are used in friction welding. Say rotary friction welding is most common, but again in the rotary friction welding the various combinations and the options are available depending upon the kind of metals or similar or dissimilar metals need to be joined. Thereafter, based on the type of relative motion which is being applied, whether it is simply rotary or reciprocating motion or it is angular motion, so based on that also some kind of the grouping or classification is done. So we'll try to talk about that as well. Here we will be starting with the issues related with the dissimilar metal joining. Using the friction welding only. Okay, so there are three areas of the concern as far as the dissimilar metal joining using the friction welding is concerned. The one is the joint interface itself. Joint interface. This is one area that is most of the time troublesome due to variety of regions. Those regions I will be talking of. Then there is the possibility of the formation of the like say unfavorable constituency, we can say. These are very poor phases which decrease the joint capabilities significantly, and so these are mostly say in form of low melting point phases. These are very brittle. Okay, and the third one is the issues that are encountered in the similar metal joining is the differential thermal expansion coefficient. So we need to apply the different approaches to deal with the issues, with the issues linked with the differential expansion and contraction. So if the thermal expansion coefficient is significantly different, say it is 10 and 18 units, so there is a huge about approximately the double is the difference in. So those which are of the low thermal expansion coefficient, they come under heavy, severe stress localization, especially along the joint interface. So we need to tackle the issues linked with the differential thermal expansion and contraction behavior. Okay, so starting with the first one, where we have to see the joint interface. Okay, joint interface. In case of the dissimilar metal joining, you may have the completely different kind of the issues, and which may range from say say one metal is aluminium or titanium or stainless steel. This is being joined with the another metal, simple carbon or alloy steel. So you may find that one metal is having very high affinity, to the oxygen, and other one is not having that much affinity. So whenever you are joining such kind of the dissimilar combination, one is having very, like say, coherent, adherent and non-porous, like the oxide layer. So this oxide layer is very intact, with one of the base metal, say the P1 or P, parent metal 1 and parent metal 2. The second one is not say that much sensitive to the oxygen or the atmospheric gases. So whenever it happens, you will find that there is always some kind of the oxide layer which is present, and this can come from the variety of the sources, including air, moisture, grease, which will be decomposing in during the joining itself due to the heat generation. So whenever these are present and these are left, if not removed properly during the joining, due to the differential deformation or limited deformation of one metal as compared to others, then these will be left as a discontinuities in the weld joint, as inclusions. These will be reducing the metallurgical bonding. Okay, so metal to metal bonding is reduced, these act as an inclusion. So basically in presence of this, your load resisting cross sectional area, this is reduced, and the second, these also act as stress raisers whenever these are present. So in general, these reduce the load carrying capacity of the friction weld joints. Okay, and that's how these lead to the compromise in the with the performance of the weld joint. So this is one aspect where, let's say, the oxides and impurities being formed in one of the metals remain there at the weld interface. Say aluminium, you have, if leading to the formation of the hard and brittle alumina, silicon Cr2O3 in case of the stainless steel. Okay, a titanium oxide. So these will be forming the hard and brittle oxide layers or oxide inclusions, which will be compromising with the quality and the soundness of the weld joint, and accordingly the capability or the performance of the joint will be adversely affected. In some of the cases, let's say some of the cases, like when we are joining the steel, say one component which is galvanized, this is one example. The second example, the steel component has been hard faced, or you have applied some kind of the coating using thermal spraying or any other method. So you see, these metals, if these are hard, and usually these are brittle, and in thicknesses ranging from say 100 micrometer to say it may be of say 5000 micrometer or 5 mm or even 10 mm. So when such kind of the components are subjected to the friction welding, the surfaces whose surfaces have been coated, either galvanized or say hard faced, or coating using the hard materials. There is a lot of difference in terms of thicknesses. This may be very thin, coatings may also be thin, but say maybe of 50 to 800 or 1000 micrometers. Hard faced layers are further thicker ones. So the one thing is this, these can be very hard and brittle, or these can also produce the low melting point constituents. So the thickness can vary, the mechanical properties can be significantly different. These can also get dissolved in case during the joining process. So the main problem is encountered in the steel or the metallic components which are coated. That is encountered because of the low forgeability of the metal which is there as a hard facing or as a coating. If it is there, then certainly this will be leading to the reduced friction weldability. You see, the ease of welding by or joining by the friction welding process, that will be reduced. Similarly, the repeatability is also reduced when you have the coatings may be of the different. So the why this is reduced, because you may come across the different types of the coating materials which are of the different quality, the different mechanical properties. So there can be a lot of inconsistencies in terms of the coatings which are there, in terms of thickness, quality, material and mechanical properties, etc. So there can be issue related with the repeatability of the soundness of the weld joint. So it will be good if all these coatings, hard facings and the layers which have been applied, these are removed. All these layers or coatings or hard facings, all these are removed before welding. So before friction welding, if these are removed, then certainly you can expect a better quality weld joint. Okay, third situation or the problem that is encountered is the formation of the low melting point constituents. It's very common, which is observed, especially when we are working with the ferrous systems and titanium. So the ferrous and titanium, whenever these are joined at the interface, these form the low melting point constituents. Another example is aluminium and magnesium welding using the friction welding. So these also lead to the formation of the low melting point. And whenever these low melting point eutectic constituents are found, these are mostly, you see, completely harder and brittle, and if these are present at the interface, then certainly these will be compromising with the load carrying capability of the joint. Okay, so we must consider this possibility, like we must avoid the conditions corresponding to which these low melting point phases are being formed, or we should try to avoid such kind of the combinations or direct interfacing of such kind of combinations leading to the formation of the low melting point constituents. And this also we can do, like use suitable films at the interface or interlayers, or use transition joint, otherwise it's still, if it is not workable. So what is that transition joint? Like this is metal A and this is metal B, and two are not compatible because of, say, this kind of reason of forming the low melting point phases. So let us bring in, either films are brought in, or let's bring in third metal which is compatible to both, and then these are joined. So this you can say as a transition metal, which will be avoiding the direct interfacing between the two, like this. So here it is A, B, and you bring in C, or alternatively you can just bring in the C in very form of thin layer as a interlayer. Okay, so here it is A, B, and C is in form of thin film or interlayer. So that also can help you to avoid the forming such kind of the low melting point phases, or it can also help to deal with the differential thermal expansion coefficient, about which I will be talking little later. Okay, so and there are some of the combinations which form very hard and brittle constituents at the interface, brittle phases at the interface, and the most common one which is known is the aluminum and iron combination. Whenever it is done, so you will see that the hardness of the aluminum XFEY kind of the constituents are formed, where your aluminum can range from 10 to 90 or 90 to 10, like this. So this changing proportion of aluminum and iron in IMCs or intermetallic compounds which are being formed at the interface, that will be changing, that will be leading to the formation of the IMCs of the varying hardness. So if you talk of like say low aluminum and high iron, it may offer you like say 200 250 HV, right? On the other hand, if you talk of high aluminum and low iron intermetallic compound, it may offer you 700 to even 1000 HV. So this is even harder. So this is even harder than the martensite, which is say 700 and 800 HV. So the formation of such kind of the hard and brittle IMCs or the compounds with these certainly be degrading the joint qualities, and again we need to use the suitable interlayers or the transition metal in between, so that you can develop the joint with a reasonably good performance. Okay, so it's very common, like you weld the low carbon steel with the medium or high carbon steel. So in that case, the problem may be the medium and high carbon steel side due to the hardenability related issues, not on the low carbon stainless steel, low carbon steel side. So this is one aspect, like when you are working with the low carbon steel, medium or high carbon steel, so that the primary difference in the hardenability will be leading to the difference in the ease of joining in these two metals. So it is possible, like the metal which is already soft and ductile, another one is hard and brittle, so you may need little preheating, let's say low carbon steel and or high carbon steel. So this is certainly harder and of the lower ductility. So in order to impart reasonable ductility as well as reduce its strength, what you can do, you can apply localized heating of the such kind of the metals which are of the low ductility and the higher strength, so that there is some kind of match between the two metals which are being joined. So maybe preheating will be good in such kind of the cases. And similarly, there is another common example where stainless steel is welded with the multiple kind of the metals, which includes like say your low alloy steels. This is one which is very common in thermal power plants. Then the alloy stainless steel is also welded with the copper alloys. This is used in like developing the different types of the heat exchangers. And then we have the titanium and the copper systems, titanium copper systems, which are also welded to the stainless steel. You may need here in some of the cases transition joint in between. So transition joint is nothing like the two metals, say SS and titanium, and in between you may bring the third one, a metal which is having the compatibility with the both the metals. Okay, so so to deal with the metallurgical compatibility related issues, or to deal with the differential thermal expansion coefficient related issues, we need to bring in either interlayers, or we have to bring in the a small piece of the metal as a transition for developing the transition joints. Okay, so one okay, so the next is here just an example. I'll give you, say aluminum. It is aluminum magnesium alloy, that is aluminum 5083 aluminum alloy. If it is to be welded with the stainless steel, so direct welding with the austenitic stainless steel may be problematic. So what we do, basically we bring in the interlayer in between. So then in that case, the aluminum, the first of all, the aluminum alloy is welded to the steel. That is different. Say you use the steel, stainless steel is welded with the say 1100 A11. So it is basically pure aluminum alloy, and then this one is further welded to the You see your aluminum alloy AA45083. So you are bringing in the transition metal or third metal in form of a small piece of the metal, or you can bring in the interlayer in form of thin films. Okay, so this is how you deal with these the issues related with the metallurgical incompatibilities and the formation of the difference in thermal expansion coefficient or formation of the undesirable the constituents at the interface. Okay, now coming to the differential thermal expansion coefficient, that's the last one. So differential thermal expansion coefficient is the third important aspect that because of which you find, like, you are joining the two metals, okay, having a large difference in thermal expansion coefficient. So say in one side it is 18, another side it is 10. So whenever there is a heat generated at the interface, obviously the temperature may go 800 or even 900 degrees centigrade. So this localized rise in temperature near the interface will be causing more expansion during the heating in the high expansion coefficient metal as compared to that of the another side low expansion coefficient of metal, and subsequently it will be shrinking more also. So because of this differential expansion and contraction, you will find that stresses are more localized in the low thermal expansion coefficient side. Okay, and whenever this kind of the localization takes place, you will find the cracking at the interface. And a common example of this is your steel and aluminum. Whenever the two are joined directly, you will see the steel is of around 22 units of thermal expansion coefficient, and aluminum is of around 22, and here it is 12. So there is a great difference whenever, and because of so greater expansion and contraction of the aluminum will be taking place as compared to that of steel. Steel is of, you see, it is of the high yield strength, although it is of low ductility. So all these stresses, whatever they are getting localized on the weaker side of the aluminum, and that in turn leads to the formation of cracks at the interface, because it is not just the high residual stresses that are causing cracking, but also the formation of the hard and brittle aluminum iron intermetallics at the interface. So you directly, whenever the two are directly joined either by fusion welding or even in uncontrolled solid state joining, you get cracks invariably. So you need much better control over such kind of things. Okay. So further, the another way out here is to bring in the third metal, which is of the intermediate thermal expansion coefficient. So say one side you have 10, another side you have 18. So let us bring in the third metal in between, which is of say 14, and then these are joined together. So the degree of the differential expansion, the extent of difference in the thermal expansion coefficient, the effect of differential thermal expansion coefficient, that will be reduced whenever such kind of things are done. So either you bring in third metal or you use the interlayers in between in order to reduce the incompatibility in terms of the thermal expansion coefficient. Okay, so now this was about the issues which are commonly encountered during the friction welding of the dissimilar metals. Okay, now I'll show you some of the things related with the further details. So this is about your this is inertia type, where the workpiece is connected to the voice and voice is further connected to the heavy flywheel. Okay. Here it is cooling down. No, it isn't. cooled. So you can see this is how the joint has been developed. So one side you have the workpiece connected to the flywheel. Okay, so this is how it is done. You can see with the clarity. This is the flywheel. Two are aligned, then rotated. Yeah, this is a initially it will be rotated and allowed to reach to the desired RPM. Then your frictional heating starts, and at the end you will see that the forging things kind of taking place. Okay, this is the rotary kind of arrangement. Okay, this one is the linear friction, where reciprocating movement is given to one of the workpiece. So at the interface, through the frictional heating, the heat is generated, and you will notice the localized rise in temperature at the fan surfaces, and that will be leading to the thermal softening. Then all the impurities will be pushed out, and you will see that the direct metallurgical continuity is established. Okay. And this is also another variant of your the linear friction, where linear movement is being given. Okay. Here this slide talks about the kind of the typical welding conditions which are used for similar metal joining. See, the similar metal joining. So the parameters which are important, the RPM which is used of spindle, you see, depending upon the metal, it can range. Like say for steel it is say 4600, for Inconel for maraging steel, for stainless steel. So the different values of the RPM are used. To reduce the heat dissipation time for copper, further higher RPM is being used. Say copper, pure copper higher than copper alloys, it is little lower. Okay, so considering their thermal conductivity or the temperature requirement, the different values of the RPM are used, because higher RPM will be generating the heat at a much higher rate. It will be taking lesser time to reach the desired temperature. That in turn will be reducing the heat dissipation, and this is particularly crucial for the high K metals, copper or aluminium. Okay, as compared to the steels. And stainless steel is having further lower thermal conductivity than the it is about half of your mild steel thermal conductivity. Now coming to the depending upon the yield strength of the metal, you need different axial forces for the friction as well as for upsetting. So say axial force being applied for stainless steel, it is in the range of 53 to this is frictional force. Upsetting force is almost a double of what is done. So although it is not very explicitly mentioned here, for Inconel it is high, you can see. For maraging steel, stainless steels, it is 80 to 90. For copper and the aluminium and titanium, these are lower. You can see for copper it is 22, for aluminium it is 27, little high for the titanium. Okay, then the flywheel size, because this was about the inertia, direct inertia friction welding. So you can see the kind of the energy that the kind of wheel size that is used in, and then the weld energy required for developing the weld joints. That is also what you can see. It is certainly lower for copper and the aluminium as compared to that of the stainless steel and the steels. Okay, and this is showing the kind of the size that is consumed, the length that is consumed in upsetting process. Okay, so this is around like say it is more for aluminium and titanium, copper, it is around 2.5 to 3 mm. And this is about the the total the time that is in welding. So this was about the your dissimilar metal welding. So this earlier what I have talked was similar metal welding, and what happens when you use the dissimilar metal welding, say copper to steel, or tool steel to the normal alloy steel, or say simple carbon steel 1045, nickel to the 1045 steel, stainless steel to carbon steel of 1020. So these are the typical values which will be which have been shown, and the corresponding RPM, axial force, the weld energy requirement, and the material loss that will be taking place, etc., have been shown. So these are certainly or of optimized values, okay. For developing the different plants, you need to do a lot of things and a lot of work for doing this kind of developing this kind of joint. Okay, so one more thing which is important here, when you work with the different metals, like say the aluminium or stainless steel, or copper with the aluminium, there will be a lot of difference in the ductility as well as their yield strength. So under the identical conditions of the axial force, you will notice that one is getting deformed and upset much more as compared to the other one. Okay, and same thing will be happening in case of stainless steel. Carbon steel will be getting softened to a greater extent as compared to the stainless steel. So they may be experiencing much more upsetting as compared to their other components. So that also has to be kept in mind, like where how much allowance is to be given for the upsetting purpose. Okay. Yeah, this is what I was talking of, depending upon the relative motion between the workpiece. You see, so we one simple thing is where rotary motion is being given. So we can call it as a rotary friction, where the cross section, you see, you are rotating both the members. Now, in which direction you are rotating, that is another thing. I will talk little later about that. So you can rotate, you see, you can keep one fix and another rotating. That's one possibility. In linear, one is fixed and another is moved like this, right? So this is simple linear motion. In orbital, rotary movement is given to even non-symmetrical components. So that's the case of the orbital welding. So if you see the kind of these are the three different cases where angular welding, depending upon the kind of, say this is one component, another component, two are to be joined. So what we do, instead of linear movement, the movement is given back and forth in a particular angle, and that movement, like say can be up to 15 degree angle, up to 15 degree with a particular frequency. Linear friction, like say the workpiece is being moved back and forth like this. Okay, so this movement, amplitude of the movement can be from 0.5 to 2.5. Okay, in the range of with a frequency of say 100 to 300 hertz. It's not in the range of ultrasonic. Ultrasonic amplitude is much lower and the frequency is much higher. So that's the difference here. And here you are the biaxial oscillation, little movement as oscillatory as well as rotary movement is being given. So with a little amplitude at a frequency of 80 to 90. So this is just for the better understanding of like what happens when things are brought in direct contact with each other. So there are peaks and valleys at the surfaces of both the sides. So these peaks and valleys will be coming in contact, and these will be getting deformed, coming closer, and this process will continue, especially in the initial stages. So that's what we call as a run-in stage, where all peaks and valleys will be getting collapsed, and some kind of the stability in terms of the surface conditioning will be realized in the initial stages. So this is just showing the kind of the initial stage contact that will be happening at the interface. if you see this diagram, this is like say the base metal, one base metal is being joined with the same base metal, so similar friction, similar metal joining using the friction welding. What you have in, like at certainly the peak temperature will be there at the interface, and on moving away from the interface, your temperature will be coming down. So this is the zone corresponding to the low temperature heat affected zone, low temperature heat affected zone, and in vicinity of the interface you'll have high temperature heat affected zone. That's one thing. At the same time, you can also see some kind of the, like say this kind of thing, where the grains are getting reoriented or getting elongated or deformed in a particular direction. Okay, so this is the zone where you have the effect of both. This you can say as a thermomechanically affected zone. Okay, this TMAZ kind of thing. So one zone where you have the heat affected zone, then thermomechanically affected zone, and the well interface directly. Now depending upon the size, if you notice, this scale is how much? 200 micrometers. So the weld zone size may be 100 micrometer or so, where you have the significant refinement or the structural transformation or the metallurgical changes that will be encountered. Okay, thereafter that you will have like say from the joint interface up to around 200 micrometer, both the sides there is a heat affected zone. That's how you can see it. Now, as I was telling, like that for even for the rotary friction welding, there are multiple combinations possible, using which you can develop a joint. These combinations may be in terms of the rotation or placement of the third material in between. Okay, so here one simple case is the basic one, where one is fixed and another is rotated. This is the simplest case. The second case, where the two components are being rotated so that the relative speed at the interface is much higher. Okay, so one is rotated in clockwise, another is rotated in anti-clockwise, like that, right? So one this side, another opposite side. To bring in the third metal into the picture, what we do, one metal, the third metal, a transition metal or third metals, let's say this is A, this is B, and you want to bring in C, then one piece of the C will be brought in, and then these two will be kept in fixed position, and then the axial force will be applied, and the middle one will be rotated. So this is called center drive arrangement, and so in this case also, you see, or the center one is kept fixed, and the metal in the two sides are rotated to develop the weld joint at these two locations. So these are the cases which can be effectively used for dealing with the problems related with the metallurgical incompatibilities of the two components or two metals to be joined, or it can also be used to join the two different metals having the significantly different thermal expansion coefficients. Okay, these are about like the kind of advantages that we get, the kind of limitations that are commonly encountered in friction welding, and the typical applications. Okay, so here you can say the advantages of the friction welding. So the problem here is the cleanliness is crucial in friction welding to avoid the presence of discontinuities, although some of these are removed. So you get the advantage of basically self-cleaning, because these impurities to some extent are pushed out, or these are burned. These are burned due to the heat generation. So many the impurities present at the surfaces, they decompose thermally whenever the heating is done, or if these are stable, these may be pushed out. So the cleaning, self cleaning, is one of the good features of this the friction welding. The second thing is, you see there is no fusion. Okay, so the possibility for intermixing is very limited. Intermixing is limited, and because of this, you find some scope for developing the dissimilar metal joining. So the scope and opportunities are much better in friction welding for dissimilar metal joining as compared to the friction welding. Okay. Further, it may be very cost effective also, in the sense that there is no use of the filler, except when you are working with the dissimilar metals, or you have to bring in a third metal in order to deal with the metallurgical compatibility or thermal expansion coefficient related issues. There is no filler, or you can use the interlayer also, but in very few cases. Okay, so actually there is no filler, or there is no flux which is used in these processes, and also, since there is no fusion melting kind of thing, so there are no fumes or toxic gas generation. So this is another good thing. Otherwise, the fusion welding is known to be very problematic because of generation of so many the harmful gases. Okay. It is doable or good for joining the metals, not possible using the fusion welding. So this is another good part, good for joining the metals which otherwise cannot be joined using the fusion welding. The automation of the fusion welding in some of the cases possible, like the GTAW or your GMAW, and then laser welding, electron beam welding. But if you see, in these cases where the fusion is to be realized, there can be a lot of inconsistencies. So what we do in case of the friction welding, you can have control over the temperature which is to be achieved, the kind of upsetting. So you are aware of, like, the kind of temperature need to be realized, the kind of upsetting is to be done, and accordingly you can identify different parameters to be used, and because of this the automation of the friction welding is very much possible easily. Okay, so easy to automate the friction welding. The process, it doesn't take very long, like 10, 15, 20, 30 seconds. So the process is very fast, and the quality is really good, and the weld cycle time is very short. So these are some of the things: short weld cycle time. Okay, now as far as the limitations are concerned, since the metal is to be deformed in the solid state, the metals may have very limited ductility, forgeability. So the forces which will be generated, the power that you need to develop a sound weld joint by friction welding, you need a very rigid, very robust machines, okay, for handling all these forces. And because of this, you will find there is an increased cost of machines. The friction welding machines may be very costly. Okay, the forging force, very large axial force may be needed for the upsetting. So you need to make the systems rigid accordingly. There is a possibility you may not be able to develop the joint designs which are possible are limited. The joint configuration or joint designs are very limited. The joint designs that can be developed using this is those are very limited. And as I said, so these are some of the limitations. uh, the rigid and robust machines, so these are very costly. You need to apply large forces, so it's possible like one component may get deformed or damaged under the effect of the heavy forces. You need to perfect work holding devices with in the robust machines, and the limited design possibilities, and these are commonly used for joining the tubes, shafts, pipes, bars, plates, etc. So these are the kind of common the things that are joined using the friction welding. Okay, so that's all I think about the friction welding I wanted to talk about.